All right, let's jump straight into this explainer on the FGSGR framework. That stands for Frequency-Governed Self-Graph Reasoning, by the way. And what this is, essentially, is an exact blueprint for shrinking down a massive, resource-heavy AI so it fits natively right onto a 2 GB edge device. We're talking drones, autonomous robots, things operating in the real world. So, if you've ever wondered how we actually move beyond these massive server farms and put highly reliable, deterministic reasoning directly into physical environments, you are absolutely in the right place.
Since we're going to follow a highly structured step-by-step journey of a single data point through this pipeline, here is our 6-phase flight plan. 1. The giant brain bottleneck. 2. Mapping data to 3D space. 3. Spectral routing via FFT. 4. Navigating expert subgraphs. 5. Inverse spatial projection verification. And finally, 6. The verifiable edge AI.
All right, part 1. The giant brain bottleneck. Escaping the memory wall.
Think about the massive scale we're dealing with today. Standard monolithic models use dense weight matrices, which basically means they entangle all their logic across billions of parameters. To run them, you need over 100 gigabytes of memory and just an incredible amount of power. But the FGSGR framework? It's built specifically for constrained hardware like an NVIDIA Jetson or a Nano. It's frankly mind-boggling when you think about it. We're talking about taking this massive 100-gigabyte behemoth and shrinking it down to under 2 gigabytes. And it does this by breaking the intelligence down into localized, completely independent subgraphs.
Because outside of just the massive storage size, standard autoregressive models have a fatal flaw when it comes to deterministic logic, right? They literally wash out brilliant edge case reasoning into these smooth, generic hallucinations. And why? Simply because the path probability decays exponentially. If a deduction requires a really long chain of rare but totally accurate steps, a standard LLM will eventually just default to a higher probability but completely incorrect semantic basin. The FGSGR framework actually eliminates this decay mathematically. By using explicit abstract syntax trees, it treats logical rules as hard algebraic constraints. So if a path is invalid, its probability is exactly 0, no guessing. If an edge case is valid, it's fully insulated from being diluted away.
Moving on to part 2. Mapping data to 3D space, leaving text behind. To pull this off, we have to stop treating data as text tokens entirely. Enter the multimodal spatial embedding layer. Think of this as a universal translator for literally any input modality. Whether the system is ingesting high-density tactile pressure data from, say, a robotic skin, or parsing an unstructured text prompt about complex math, it projects those disparate inputs onto a uniform, continuous 3D coordinate space. This is absolutely crucial because it prevents phase alignment errors when the system inevitably has to mix different types of data.
So an unstructured prompt or a raw physical sensor feed is literally converted into a three-dimensional spatial tensor, anchoring it physically. The input gets mapped into a hard X, Y, and Z coordinate grid. So the data is no longer just this floating concept in an arbitrary embedding space, it has actual physical geometric volume in the system's memory.
Part 3, and this is a big one. Spectral routing via FFT, the prism metaphor.
So how do we navigate this brand new physical space? Because we definitely don't want to rely on some clunky, slow LLM classifier acting as a middleman. This is where spectral routing comes in, and it's brilliant. Just like a prism separates white light into distinct individual colors, this 4-step pipeline cleanly breaks down our physical spatial data into deterministic frequency waves. We take that 3D tensor, run it through a 3D fast Fourier transform, convert the space into a frequency domain, and then simply identify the power spectral density peaks. The 3D FFT diagnostic engine executes this transformation as a discrete matrix multiplication layer. And because Fourier transforms are highly parallelizable, this mathematical operation is perfectly optimized for immediate tensor acceleration. We're talking executing in less than 1 millisecond. Just like that, the 3D physical data is transformed seamlessly into a highly structured landscape of frequency waves.
By looking at the topographical peaks in this new spatial frequency domain, the system knows exactly where to send the data. High-frequency physical transients, say a sudden spike in tactile stress on a robotic arm, form distinct peaks that route instantly to a physics or transient subgraph. Low-frequency continuous patterns, like a logical deduction, form entirely different peaks that route to a logic or code subgraph. This is spectral routing in action. The peaks dynamically and deterministically assign the routing weights, completely bypassing the need for a massive LLM to quote-unquote decide where the information should go.
Part 4.
Navigating expert subgraphs, the AI with a pulse.
Once routed, these expert subgraphs remain incredibly small and perfectly stable because they're wrapped in mathematical shields called Markov blankets. Basically, this means the internal logic of a coding expert can't cross-contaminate the internal logic of a physics expert. By using variational message passing instead of exact inference and tightly bounding how those messages pass across the blankets, the system completely eliminates loopy belief propagation, which is a fun term for when an AI gets caught in an infinite loop of divergent overconfidence. And by utilizing a strict 2-4 structured sparsity on the hardware level, the total active computing footprint drops safely to about 0.47 gigabytes. It's incredibly lean.
The system actually acts a lot like a biological nervous system with a pulse, using this 5-way metacognitive grid. It doesn't just run at max power constantly. It dynamically ramps energy up or down based strictly on the current uncertainty, what they call variational free energy, in the environment. State 1 is just quiescent, low-power self-cleaning. State 2 is standard active inference. But let's say there is a massive spike in uncertainty or conflicting logic. It instantly ramps up to State 5, emergency convergence, maximizing its compute throughput to force an immediate resolution. It literally breathes with the complexity of the task in front of it.
Part 5. Inverse spatial projection verification, checking the math.
We've routed our waves and processed the logic, but we still face a massive hurdle before we output anything. Standard AI would just sample a bunch of independent text paths, execute a majority vote, and basically cross its fingers and guess, which is computationally expensive and dangerously open loop. But FGSGR demands actual mathematical proof. So how do we ensure absolute causal integrity? This is where the true elegance of inverse spatial projection completely changes the game. Because the system is built on bidirectional factor graphs, it can literally run its generated output backward. It uses an inverse 3D FFT to reconstruct the original input coordinates purely from its own conclusions. Then, it calculates the prediction error between that original input and the reconstructed input. If the error is too high, the system immediately knows the logic is flawed, and it prunes those specific nodes using Bayesian model reduction. It verifies itself mathematically in a closed loop within a single inference cycle. No generative sampling overhead required whatsoever.
Under the Brett-Goodwin protocol, truth in this framework isn't just a static fact. It is defined as parsimony that persists. Through the brutal mathematical cross-examination of inverse spatial projection and Bayesian model reduction, any unnecessary parameters or hallucinatory jumps are analytically pruned away. The logical path that remains, the most efficient, structurally sound explanation that correctly predicts the inputs backward and forward, that is the truth. Finally, Part 6, the verifiable edge AI, bringing it all together. Tracing this complete pipeline from start to finish, you can really appreciate the awe-inspiring elegance of this architecture. Unstructured data is ingested. It's embedded into a 3D spatial grid. The diagnostic router converts it to a frequency map, where spectral routing instantly sends the data to Markov-blanketed causal subgraphs. The metacognitive grid scales the compute power based on urgency. And finally, inverse spatial projection ensures closed-loop verification, outputting a certified, deterministic response. The whole shebang.
When you look at the raw numbers side by side, it highlights exactly why this matters so much for our future. Monolithic LLMs require over 100 gigabytes, suffer from that exponential edge case decay, and have wildly high latency. But through the FGSGR framework, we have effectively achieved sub-50 millisecond deterministic reasoning inside an incredibly tight hardware envelope of under 2 gigabytes. We've completely replaced intermediary LLM routing with instantaneous spectral routing, and we've replaced open-loop guessing with bidirectional inverse spatial projection.
So, as we wrap up this explainer, I want to leave you with this final provocative thought. We have fundamentally shattered the memory wall that was holding back physical AI by using spectral routing to instantly map complex environments and inverse spatial projection to mathematically guarantee the actual truth of its reasoning. We are no longer tethered to the server farm. The unbound future of localized edge-based machine cognition is officially here. So what impossible frontiers will autonomous robotics conquer next, now that they can truly, reliably think for themselves right on the edge? Thanks so much for exploring this with me.